right. Whoops. Let me get my video up there. So our goal is to analyze rotational motion, and we want to do rotational kinematics to start, and we want to do it with coding. So where is that? Where did it go? Whoops. Oh, that's meta. All right, there's the one I wanted. All right, so our goal is to look at this code, and rather than just go through it, I think it will help if I start from scratch and understand this code. So I've got it copied over here, and we're going to recreate this code from scratch. So if you have GlowScript open, let's do it. Let's call this rotation test 3, just to give it some random name. And so where did that go? Did I not hit the right button? Sorry. Where is it? Did I lose it? Okay, this is weird. All right. There we go. All right. Okay. So now in this case, I'm just going to start by creating a ball. Actually, let me copy some of this, and then we'll talk about it. And we don't need the ball to have any mass. So I created a ball, and I just said ball equals a sphere. And maybe I'll zoom in a little bit in case it's grainy, just so you can see it a little better. All right. And so I'm going to, let me back that to there. All right. So hopefully it'll stop being grainy in a minute. Just give it a color and a position. And right now I'm going to give it a position, say -1. All right. And before I get too far along, I'm going to run it and see what this looks like. It should be cyan. There it is. We got a ball. Great. Now, ultimately, this is going to be our pivot point. So if you want, you could have called this pivot, and I think that's what I do in the other videos. But for now, just know that the ball is the pivot. And then just to save us a little bit of time, let me get this up here. For me, it's kind of nice to have some coordinate axes on the screen. And I guess I could label them as well. But for right now, I want you to notice that there's going to be a red axis. So the X is going to be red, and the Y axis is going to be yellow. And again, before I get too far along, I'm just going to run it. There we go. You can see it. All right, so I'll pause for a sec while you guys get that fired up. Again, that's just so we have some objects there. And now I want to create an object that I'm going to rotate. All right. I'm worried that I'm going too fast because I did a lot of cut and paste. So maybe I'll wait for a second.
Yeah. Can you wait a little?
Absolutely. I should have just typed it out so I was slower. That's my bad. I'll do that going forwards.
Are you going to do the pendulum as well?
I'm not going to do it, but I think all the pieces you need to do it yourself are here. Was that Jose?
Yeah.
No, Jose, I'm going to basically redo what we did the other day. So all you have to do for the pivot is you need to compute alpha from torques, and then it's exactly the same as what we did before. All right. We can talk about that at the end, how that might work. Is that cool?
Sounds good.
So if you want, you may not want to watch this if you already know it all. And then, because Jose and I did this the other day and I forgot to live stream it. All right. Or Jose, if you want to just take a break and come back, that's cool. Or do whatever you want, or struggle, or anything.
I'll stick around.
Got it. Okay. Is this a good time to head on, everybody? Whoever spoke up earlier, did you get caught up?
Yeah.
All right. So now I'm going to create something I want to rotate. Actually, oh, geez. All right. If it does this to you, geez, go figure. I'm going to just copy this and refresh it and see what happens here. All right, there we go. Line X. Actually, let's call it a rod. Let's call it a line X. Actually, I'm just going to call it a line. Sorry, I keep changing my mind here. So I'm going to give this, I'm going to define a cylinder this way. Let's say its radius equals 0.5 again. And its position is, let's put it at, how about -2, 0, 0. So it's going to notice this puts it at the same spot as the x-axis here. All right. And so I'm just going to make this only 3 units long instead of 4 units long. Now, what's going to happen in the code, first it's going to draw the ball. Then it's going to draw these 2 axes. And then it's going to draw this line. So it draws them in order. And because this one's drawn last, it's going to overwrite the existing one. And when I run this, oh, whoops. Let's make that 0.5. There we go. Now we see the white and the red mixed because it drew the white one first. And so they're kind of mixed there. All right. So hopefully you could see that all right. Next, what I want to do is I want something to rotate. I don't want the coordinates to rotate. I don't want the ball to rotate. I want this line to rotate. So I'm going to define something new. Let's say it has some angular acceleration. And let's say that angular acceleration is a vector. And now we have to be careful. Because it's a vector, I want you to specify the numbers here. So let's say 0, 0, 1. Which way is this thing going to rotate if I do 0, 0, 1? About which axis will it rotate?
Z-axis.
Z-axis. What if I instead do that? It will rotate about the y-axis. So, all right, we've got it. And let's make this number 2 just for fun. All right. Next, I'm going to give this thing. And so this is the initial angular acceleration. In this particular code, I want that to remain constant. But Jose, what's different about your code is this number will have to be updated in the loop each time the rod moves. Got it?
Got it.
Okay. So I'm going to give it an initial angular velocity vector. Let's say it's 0, 1, 0. So there we've got that. And all right, so let's do that. And now let's just take a look at this thing. It shouldn't do anything crazy. Let's just run it and make sure it saved everything. All right, so it's not rotating yet because I haven't introduced a loop, but it looks like it's drawing everything okay. All right. I'm going to change that to 1.5. All right. Now I want to teach you how to rotate stuff. Now, I'm not always going to be there for you when you need me, so let's teach you how to find stuff yourself in the help file. If I want to rotate something, and I've never done it before, I would probably go to the help file. And I would say, well, I don't want to draw something. I want to work with it that's already drawn. So I go in here and I say, rotations. And notice what is required. I need an angle, I need an axis, and I need a pivot point or an origin. Angle, axis, origin. I'm going to write that down. I need an angle, I need an axis, and I need an origin for the rotation. Those are the 3 things. Obviously, there's going to be defaults, the default is usually, if I'm not mistaken, it's the z-axis and the origin is 0, 0, 0. So if the minimum that you need to specify is just an angle, right? So anyways, all right. Or, oh, that goes to the object's position. So never mind. I was wrong anyways. So yeah, for me, it's better to actually state these things in particular rather than using defaults. Okay. Let me get out of there. Let me do this, get rid of this, this. All right. So let's go back to here and let's run this program and think how we want to rotate this thing. If I want to rotate this thing, I need an angle and an axis. We've already talked about we want to rotate. I think I said the y-axis, didn't I? So the trick is, let's use this thing right here as the pivot point. So the origin is going to relate to this spot. What's a good way to reference that spot?
Ball.position.
Ball.pos. That's going to be our reference for the origin. So I'm just writing this down up here in the upper left, just so I've got it. Now, what is the axis we want to use for rotation? We want to use something parallel to the y-axis. Now, vectors can be moved around. What is the simplest possible vector you can think of that I drew right here with a yellow arrow? I don't know if you could see that. What's the simplest way to express that yellow arrow in code? Let me ask you this. What does that look like? 1 in that direction. What do we usually call that?
The y component.
Yeah. Isn't that just j hat? 1 straight up?
Yeah.
So how do I code j hat? What do I have to type again?
Vec.
Whoops. And then what do I type in?
0, 1, 0.
Correct. And then somehow it looks like I drew a minus sign. I was not intending to do that. Let me get that out of there. Okay, there we go. And then the angle, that's just some number. All right. Now we got to be careful here. When we type in the angle, I'm just going to write that here down below so I could see it better. The angle, usually we think in degrees, but we need to convert it to radians. All right. So those are the key elements we need to understand just to do a rotation. And once we can do a single rotation, we can add that into the loop. So let me clear out some of this stuff. All right. And let's get rid of this one up here. And then let's go into the code. So let's say I want to rotate this object and I want to rotate the line. I would say line dot rotate. I'm going to put both of my parentheses right away, then go back, and I know I need an angle. I know I need an axis. Oops. And I know I need an origin. Now, again, you could trust the defaults, but I always find that dangerous. So now I know what I need to do. What angle do you want to use? Pick an angle. Pick an angle.
60 degrees.
Okay, so let's say I'm going to do it this way. Angle in degrees equals 60, right? So I need to get the angle in radians. Take a guess what command I use.
Rad.
Radians, close. So radians is the command to change it. How could I check if this is working right? Before
Print
I
it.
do, you could print it, right? Now, I don't know 60 degrees that well, but I know 180. What should the print statement say if I use 180?
Pi.
Pi. So let's do it. And I'm just going to give myself a little space here. So when I run this one, I'm just making sure it works. Is this, oh, whoops, because I didn't, okay. Let me I didn't actually work all this. So I could comment this out. Where'd that go? And now let's run it just to make sure this is working. Looks like it's working. So now I could go back to that 60 degrees that somebody said. All right. And now I don't really need this print statement anymore. I'm confident that it's working right. So let's go back down to here. And I want to pause. Am I going too fast or is this okay? Is this too slow? Remember, at any time, if I'm wasting your time, just go do the quiz. Okay. All right. So the angle, I need to use the angle in radians, not in degrees. That's the issue. One of the issues that we have. The axis, I'm going to just say 0, 1, 0. That's going to be about the y-axis. Now, perhaps we could do this better like this because we might be using this axis all day. Maybe I'll just define it here. That way, if I want to use it over and over later, I don't have to keep changing it in every occurrence. So now if I want to use this thing later, it's pretty easy to step this up. This may have some, when we get to the end, this may be useful. That's basically how I'm going to say it. And then here, somebody said ball dot position. All right. So what we did is we created a ball, we drew some axes, and then we drew this line and we made some properties for it. We still have not used the alpha and omega yet. But first, we're just going to try and rotate this thing to some initial angle. So we're basically setting up the initial angular position. We're rotating the rod. Let's run it and see if it works. Now, in this case, you can't really see it. But if I rotate to the top view, you can see it, right? And notice it's not rotating about the origin. It's rotating about the ball dot position because that's what we called the origin for the rotation. If I go back into here, if I change the orientation, like we could change this to, how about just, if I run this about the origin, see how it's rotating about a different spot now? So the idea is this is useful. We could rotate things about different spots. I'm going to go back to ball.pause because that's what I wanted to do. All right. Any questions about that single rotation? All right. Let's make this animate now. So one of the things I like to do is I'll put in a time and a time increment. Oops, let's just say 0.1. Let's do this quick. And then you don't have to do this, but for me, it always makes sense to specify a sim speed. Just because sometimes the animations run too fast, too slow, you want to be able to speed up or slow them down. And let's just do a while loop. Oops. Where'd my loop go? Just making sure I'm not, while t is less than 6. Obviously, if you want to make this move, you need some kind of a loop. But if we're going to specify a loop that's based off time, we need to set the time initially to 0 and specify how much each frame is in terms of the time interval. So we're initializing the time to 0, we're setting a time increment, and we're setting the speed to 0.5. I should warn you, I'm not doing a good job of commenting on this code. I'm more interested in you learning. So if you need to make extra comments about like so you can understand this later, feel free to add all kinds of comments in here. And I apologize for not making many as I go along. I'm not really emphasizing good habits. Sorry. Whoops. Next, I like to do this. What that does is, again, you don't need a rate statement. If you don't put the rate statement, the computer will just run as fast as it can. However, when we're animating things and visualizing, it is nice to put in a rate so we can see things at real speed or half time, etc. Right now, I'm set up to run this thing at half speed. All right, now we get to some physics. Finally, we're at some physics. I need this thing to animate, and I know these two pieces of information. I know alpha as a vector, and I know omega as a vector, right? So does anybody know any equations that help me understand? And I also know, notice this, I also know theta initial. Do you see that? Does anybody know any equations that relate these variables to time?
We know alpha is the rate of change of omega over dt.
It's d omega dt. Now, if I rearrange this or use an approximate form in a computer, we can't use it infinitely small. But if I cut up the time step small enough, it's delta omega over delta t. Okay? If I rearrange this, notice the change in omega is alpha delta t. I expect you could probably believe me if I rearrange this into the normal way we've seen it in kinematics. This is just V final equals V initial plus AT in rotation land. So if I want to put this statement in there, right? The idea is if you're accelerating, omega should change, right? If we have an alpha, shouldn't the omega change? We don't want this thing to rotate with a constant rate. We want it to rotate and change its rotation rate. So how could I put that information in the code? What should I type? Somebody take a stab at it. It's okay to be wrong.
Could you do line dot omega plus equals line dot alpha times dt?
Let's take a look. This plus equals means change omega by this much. That's actually this line right here. Well, it's not quite that line, right? There's delta omega, right? So this is saying take the old value for omega and add to it the change. And that's exactly right. Let me rephrase this another way to see if this makes sense, because this is a big deal if we can learn this and really understand it. I like to think of it like this. Everything between the plus and the equals is absorbed in this plus equal sign, right? We take the old value of omega and add to it this, and I output the new value. So this is called the velocity update equation. In this case, it's an angular velocity update. That's sneaky, but any questions about that? I'm just cleaning things up. And then I'm going to run out of stuff here, so I'm going to get these out of here. What's the next thing I need to do? Well, let's look. We want this to animate the rotation, right? So let me scoot down just a little bit on the page here. Let me get a couple of extra lines of code. There we go. So now I want this thing to rotate. Look at line 22. I need it to rotate. I know the rotation axis already. I know the origin already. Is the angle I need to rotate it going to be 60 degrees? What do you think?
No.
No. How could I calculate the angle? Does anybody know another kinematics equations that maybe talks about angles? Here we talked about alpha and omega. Is there something that gets theta involved? Somebody else?
Is it omega is equal to delta or d theta over dt?
I like what you said first, the deltas, because I'll just skip right to it. Do you agree that it's approximately equal to delta theta over
Yeah.
delta t? Probably one of the most confusing parts of this code is right here. So this is sneaky. The trick is when you rotate something, you have to rotate by an angle. So what we have to do here is I can't just get a new value of theta and plug it in. What I need to do here is I need to plug in delta theta for every other angle. So in this case, I need to solve this for delta theta. And that I'm going to rotate it by a small change in angle. And this is very tricky. So delta theta is equal to omega times delta t. So we have not yet defined delta theta, but we could do it in the loop here. So let's create a new parameter, d theta. What should I type? Somebody new. Give it a shot. It's okay to be wrong. So instead of rotating by 60 degrees, I need to get a change in angle based off this new value of omega from line 29, using this equation that I've drawn on the right side in dark blue. Using this equation that I just drew an arrow to. How do I type that using the stuff that we've already used in the code? Somebody take a crack at it.
Line dot omega times dt.
Now I just want to, whoops. Okay, it turns out this is not going to work. And this is probably going to frustrate you. Why? So I'm going to first show you, let's say we thought this was going to work. What would we do? We'd copy this line of code. And then instead of rotating this by angle in radians, I would rotate it by d theta. Now, to be clear, you might be saying, what about degrees? What about radians? I am assuming these numbers here are in radians per second. Oh, whoops, this is radians per second squared. And this would be radians per second. That would have been a smart thing to type in a comment. Agreed? That way, if somebody's reading this later, they might be saying, well, how come you're doing degrees and then radians? And what if you had put a comment in your code clearly specifying the units of your parameters? That could help someone else understand. It could help yourself understand a month from now. All right. Now, let's pretend we think this is going to work. I'll fix the problem in a second. So to be clear, line 30 is mistaken. However, let's say we got this right and we wanted to watch this thing now. So there's one last piece that I need to do every time I do a loop. What do I have to do after all this?
Update time.
Yeah, so t plus equals dt. All right. And just to give some space here, I'm just going to spread that out a little bit. Whoops. All right. Oh, and now my annotations are all off, but whatever. So let's clear my annotations and run this. And I claim you're going to get an error. Does anybody know what the error is going to be? Why does this line give an error?
Does it have to be converted into degrees?
Nope. We want it in radians.
Isn't line dot alpha or line dot omega a vector?
Yes,
why?
line dot omega is a vector. And so I don't know if you noticed this before. Look at the number. You have to type in a scalar for the angle, positive or negative, but it has to be a scalar. Omega is a vector. So what is d theta going to be in this particular code? D theta is going to be a vector, which then this line should give us an error. Now, let's see if that is true when we run it. Doesn't know how to do it, right? So when you put that, that's what that, notice it doesn't give you the right error message. It's not saying you put in a vector where you're, but you're supposed to say, huh, that's a very confusing error. So, all right. To be honest, if you think you're good now, you can go off, but I think you're going to find there's a couple other tricks that have to do with this in a minute. So one thing you could do, we could just stick a magnitude on here. Why is that a bad idea?
Could be negative.
Yeah. If we look up here, what if omega was -1? It would totally ignore that minus sign. So one other way we could do this, well, we could do this. We could just say line omega dot y. Agreed? That would pick off the y component. What's another way we could do that? Does anybody have, this is a little bit different. I'm just going to tell you. What could I dot this with so that I get the right component?
Vec 0, 1, 0.
Do we already have that written somewhere?
Oh, rot axis.
Rotation axis. So this is useful because what if we wanted to change the problem later and do a different rotation axis? We got it. You know what I'm saying? So instead of having, so now if I change this number, and in fact, maybe it would have been smart to do this. Maybe we should have done this. We should have specified the rotation axis right up here at the top. And then what we could have done is we could have said alpha is equal to 2 times the rotation axis, right? And omega could be -1 times the rotation axis. And now if I redo this code and I want to do it about a different axis, I only need to change one number and everything will update. Okay. That's just, yeah. Did I go too fast there or any questions? Let me pause here. I'm going to zoom out. Is this helping at all?
Yeah, I would say so.
Okay. I don't want to waste your time, so I'm just trying my best here. And yeah, it's tricky. Let's keep going. All right. So after all that, let's make sure I didn't screw anything up. I've done a whole bunch of stuff now. What did I do here? Let's see if this actually works. Anyways, this was a different way to do it, right? This picks off the component of omega that's parallel to the rotation axis. Let's see if this works. Did you see that? It looks like it's working on my machine. I don't know if you could see that at all. So this is going for a really long time. I'm going to make this a shorter loop. I'm going to make it slower speed. Let's do 0.25, quarter speed. And then I'm going to emphasize this. I'm going to make sure this omega is negative. So when I run this thing, see it going backwards? And it should start slowing down. And it's going to reverse direction. I have no idea how long this takes to show up on your computer because of Zoom lag. I'm going to make this loop a little longer here. Sorry, I'm scrolling so quickly. I'm going to try this one more time. We keep missing the first part of the motion. Do you see that? I can't rotate the screen quickly enough. It's already started rotating and slowing down before I could see it. Can you think of any? Wouldn't it be nice if we could wait for the computer, or if the computer would wait for us to click or something? Wouldn't that be nice?
Yeah.
I happen to have a line of code here that I read the help file. Check this out. Sometimes I'll add this to my loops. So I'm going to wait for that to show up on your screen. Line 28, scene dot wait for click. It's going to wait for me to click the mouse. So when I run this, check this out. I can zoom to whatever I want. Now I'm ready to click. Now I've clicked. I could see the whole motion. Here's that line of code again in case I did that too quickly. I hope you find that useful, because now you could make, and you could put it, you could stick in an if statement, right? Like every 1 second, you could say, if the time is between 1 second plus or minus dt over 2, wait for click. And then every 1 second, you could pause the screen or something. There's all kinds of ways you could use these events wait for. If you are a computer science major, these wait commands are used in multi-threading, meaning parallel processing. If you want one processor to wait for another operation to finish on a different processor, so yeah, there's some serious stuff in here if you work at it. All right. So far, so good. But now, I think, Trey, would you say the hardest part is drawing the arrows after this?
I'd say so, yeah. Once you get all the vectors figured out, it's drawing the arrows and then getting the arrows to update that becomes the new challenge.
Okay, so before we get to the last beefy part of here, any questions here? I'm just looking at your faces now, or I'm looking at your screens. I'm looking at Trey's face and a bunch of names. Any questions? All right, let's get in and do it. Sorry it's taking so long, but all right, let's just get it over with. All right, so now let's say I want to draw, let's get into here. I'm going to show you this. I'm going to rotate the screen. Remember, I haven't clicked the mouse button yet, and I want to annotate on here. We know that this is going to rotate this way initially because omega initial was negative, right? Let's say I want to consider a spot on the end of the rod. What does that ball's velocity vector look like? Just kind of describe it to me. Is it up, down, right, left, some combination? What is the velocity? Not angular velocity, velocity.
Down and to the right, maybe?
I'm with you there. Do you know any equations that relate velocity to omega?
The velocity equals radius times omega.
Right on. So I'm going to write that up here in velocity equals r times omega. Now, this equation is not a vector. I don't need the speed. I need the velocity vector. So in this instance, what does r mean? What does r mean here? Go ahead.
The distance between the pivot and the area on the rod.
So like this?
Yep. but not the
No.
other way.
Exactly. It's from the pivot to the point where we are interested. So I deliberately do that wrong, and that green did not show up. So let's see if I can find a brighter color here. This is the R vector that we care about, right? So we have omega, V, and R. How do you think those relate? And I just want to point them out. They're all three vectors.
Cross product.
There's got to be some kind of cross product. Why did you say cross product?
Because omega is in the opposite perpendicular direction.
True. Omega, right? So if we think about this, omega vector is pointing out of the page as I see it right here. Or if you recall, it's going to be in the, I think we said it was in the J hat, right? And so it's very tricky to do this in general. We need to figure out how to, two things. How do we write these three vectors using statements in code? And then which things do we cross with which? So if you had to guess, Esteban, what cross product would you try to use?
Actually, for that omega, wouldn't it be pointing into the page since that one is clockwise?
Oh, shoot. You're right, Trey. Thank you. Thank you. That was, I was wrong here. Trey, thanks for fixing that up. I wasn't paying attention. This should be an X, so it should be a negative J hat. Thank you. Good call. And now I'm going to switch to just black over here. So what do you think? Here's another way you could know it's a cross product. If you want to multiply two vectors, if I do a dot product, the output is a vector or scalar?
Scalar.
Scalar. And we don't want a scalar output. We want a vector. So now I'm going to ask you a question here. Give me just a second. There's two ways we could do the cross product. We could either do R cross omega, or we could do omega cross R. How could we figure out which one is correct?
The wheel of pain.
You could do it that way. I was also going to just say, try one, see if it looks right. And if it doesn't look right, try the other one. That's now the wheel of pain would also work. Do you agree? So let's just try one and see. So I don't know which one of these it is. Well, I do, but let's pretend we don't know. So rather than overthink it, there's only two possibilities. They're going to be off by a minus sign. Let's just go try one. So let's, let me clean up part of this. Oh, shoot. You know what we should have done? What is the R vector here? Let's talk about that before we go back into the code. Let's talk about this. Am I drawing? There we go. Let's talk about this R vector. Right? What's a good way to describe this R vector? In the code. Well, let me ask you this. Let's first define this position in the code. How could I define this position out here? What's a good way to describe that? Let's call that the tip of this. Okay. How do I describe the tip?
We do rod dot pause plus axis.
Yep. And I think we called it line, didn't we? I think in our code
Yeah.
it was called line. So does everybody agree that says start here and then go over to there, and that will specify the tip? Is everybody okay with that? That's sneaky. I hope you're okay with that. So now, how do I define the R vector? It's from what to what? What would I write next?
R equals ball dot pause plus tip.
I would say the axis. So what you just wrote there minus the ball dot pause.
I would say, yeah, tip minus ball dot pause. And let me explain why. I think the other one might also work, and I haven't thought about that. It might be just but the idea here is this is the final position, and this is the initial position. So usually in the vector, we go final minus initial. And that's what was going on in my brain. That other way may have worked. However, well, let's just look at this particular one. I don't think it would have worked because right now, let's say this tip looks about like vector, comma 0, comma 2, comma 0. That is the location of the tip. It's approximately 2 units above this. Oh, shoot. Oh, crap. This is like, actually, it's in the Z direction, I think, because we rotated the screen. This is when it's nice to have labeled axes. But I just want to point out, if you did the ball's position plus what the tip is, you'd actually be right here. That shouldn't work. Does that make sense, whoever asked that question?
Yeah, it makes sense.
Yeah, because the tip is a location in space, but it's also a vector. A position describes a vector. In this case, the tip describes just that. That's tip. So ball pause plus tip is not the same as R. All right. All right. So now we know how to get the R vector. And I think the V and the omega, we've already got that figured out. We'll do that in there. All right. So now let me clear this up. I think in the code earlier, I did rods and bugs instead of lines and tips. So it'll be a little bit different when you watch the other video, but it's the same kind of crap. Okay, so let's go into here and let's use this information to code this. So rather than try and do it inside the loop, let's try and do it before the loop. That way we've got this click in here. That way we could just see if the first one works. If we can't draw one of these, what's our hope of doing the entire thing? All right, so let's get this in here. So first, let's define the tip of this thing. And we said that was equal to line.pause plus line.axis. That describes the tip of the line that we have. Next, let's define this R vector. I'm just typing in the stuff that you had me write down. And next, let's get we could name this more cleverly later, but let's say I want to get the velocity now. How should I do that?
Use the cross function.
And then let's just try the first one. What's the omega? How do I get omega?
Line dot omega.
Yeah, I can't just type omega, right? Omega is not going to work because we referenced it in the, it's an attribute of this line here. Okay. And then when I do that, how can I check if it's actually working? The computer's going to do something here, but is it going to output anything?
No.
No. So we need to draw the arrow, right? All right. Where should the arrow be located? What is its position?
Tip.
At the tip. Where, let's see, what is its axis?
V.
V. And what is its color? What do you want to call it? How about just white? Let's forget about the color, okay, for right now. Now, let's run it and see if it works. Is it at the right location?
Yep.
No.
Yes. It is located correctly. Is it pointing the right direction?
Nope.
No. That's so right. The position of an arrow is its tail. The position is at the tip like we want it to be, but it's pointing the wrong way. So what does that tell us about my cross product? This one's wrong. If we switch it, it should flip the sign. That's what happens when you use cross products. So let's try this. We'll switch it. It's running. We've got it to look right. Because if you recall, in this particular one, it's rotating this way. Now, some of you might be saying, gosh, I wish I could draw that arrow smaller. I am going to work on that when we do chapter 13. Okay, so can we please just worry about the sizes of things in chapter 13? And that'll be the new piece of coding that we learn in chapter 13, all right? It's just called scale factors and saturation values, and that's one of the focuses of that lab assignment. Let's worry about it then, or once we get started if you can't help it. What do you think? So far, so good? We're almost there. Now, I want to do this inside the loop because, again, if I run this, if I click this thing, let me get this up here. If I click it, it shows me the initial value of omega, but the arrow is not, this is not very helpful to someone if they want to understand this stuff. We want the arrow to change in size and location every time. So clearly, there's all of these lines of code between lines 1 and 31 were necessary to set up the loop. Not all of them need to be put inside the loop. Which things need to be inside the loop now? Which things do I need to add to the loop so that the arrow updates?
The arrow.
I need to do this. If I do just that, will it update?
No.
No. What else needs to go in there?
V.
This has to go in there. That would give me a new omega each time. Well, let's see what this looks like if I just take these two. Take a guess. Is this correct if I just put these in here? Now, this is not the way to do it. What will happen here is it will get a new value of V every time, but it will draw, this should, I believe, draw the arrow at the tip. Has the tip calculation updated?
No.
No. So we better bring that in there too. And in fact, we better update the R value. So I think all of these need to go in there. Now watch your indents. So the idea is, here's what happens. We have a value for angular acceleration. We use kinematics to change its angular velocity. Once we have the new angular velocity, we use that to figure out how much the angle rotates. And we get a small amount of angle through which it rotates for a small amount of time. We rotate the rod by that much. Now we have a new position for the line and a new axis for the line, so the tip should be at a new location. That means the R vector will be different because the tip is different. Whoops. Now the velocity will be different because both omega and R are different, and the arrow will be different. Now this line is a bad idea. If I do this, let's see what happens. It looks psychedelic. I should have dropped more acid, but that's not what I want because now I can't see anything. Do you agree? The issue here is when you put that whole line of code in here, it draws a new arrow every time. This is not what we want to do. What we want to do is instead just update that arrow. How could I update the arrow instead of drawing a new arrow every time?
Update v_arrow.pos and v_arrow.axis.
What is the new position of the arrow? Where should it be located?
The tip.
And what should I type in for the axis?
V.
V. Now you may be saying, well, how come you put the whole thing for V in there, but not the whole thing for this? The idea is V is just a number. When we run this, the computer says, take the old value of V and replace it with this new value of V. And this says, take the old value of the axis and replace it. So when I run this, hopefully you could see that go. What do you think? Wow, we're an hour into class. This is going a little longer than I thought, but is this helping you succeed? That's all that matters, right? This one is so tricky. I just want you to succeed, right? And I want you to actually understand this. Is this helping?
Yes.
You're still here, so I guess it's okay. Trey, any thoughts you have? Any questions or comments you want to make about this, or?
No, it's all been good. Yeah, I've definitely been following along and checking my own code as well, just making sure that everything works.
Yep. Okay. Yeah. And so my videos, first it was 20, then it was 40 minutes. Now it's an hour. I want to keep going and show you one more thing. All right. I want to talk about it on the screen. And this is the piece I kind of did most of the work of this, except for one last, let me do something here just to make this easier to see. I'm going to make this a lot smaller. Let's say 1.5 and just run it. All right, so now I could see this all. Okay, I want to go back to some of the symbols we had, and I want to talk about what I need you guys to do for the quiz, the lab quiz, right? So you're supposed to get the accelerations. I just talked about velocity. I wanted you to figure out how to do the accelerations. So I want to give you some hints on that and then set you free. And then I'll even address the question, what if alpha needs to change for the pendulum code? Sorry, why didn't I just hit clear all? There we go. Sorry about that. Okay, so let's go back in here. We know that this in particular is omega. And just for right now, I'm going to say that's equal to some value omega in the j hat. Remember, we rotated the screen. So if it helps, this is a case where j hat is out of the page. And then which way is I hat? I think that was this one, right? So wheel of pain, which way is k hat?
Down.
Yes. Remember how I said always check your coordinate systems? You may have thought I was stupid, like, oh, you're never gonna. Here's a weird one that just happened by chance. It happens. Always check your coordinates. If you're wondering why earlier I knew it was in the negative k hat, it's because I did that in my mind. Always, always, always check your coordinates. This is a weird one. So what? All right. We said this over here is the velocity vector. And now, what are some accelerations that we might want to learn about? What's one type of acceleration we could learn about? I guess in this case, we also know there's alpha this way, right? What other accelerations do we discuss?
AC.
AC. What's an equation you know for AC?
R omega square.
Okay, that's one way to do it. What's another way? Somebody else.
V squared over R.
Those are the two classics. Either one will work. In rotation land, you might think the first one seems like a good idea. Now, what do you notice here? Aren't these all scalars? That's not going to help you draw an arrow. So what is AC vector? It's R omega squared in which direction?
Towards the pivot.
What's a good name for that direction? What did we call
Radial.
this? This vector right here.
It's R vector.
So what's a good name for this direction?
So parallel to R vector. So dot R dot W, or I'm sorry, R dot omega.
What's a good way to specify any direction for an arbitrary vector in three-dimensional space?
R hat.
Yeah, and in this case, it would be negative R hat, right?
Oh, okay.
You know what I'm saying? Don't we already know what R is?
How do you write that in code?
Take a guess how you get the hat of a vector in Python. What would you type?
Oh, is it just hat?
Hat.
Oh.
That was, I don't know if you remember, this was one of the questions I asked on a previous quiz.
Yeah, I don't know what I'm doing.
Yeah, so it's, you don't learn it till you've done it many times. Right, Trey?
Definitely. Yeah. And even then,
Is this making sense to you, Trey?
it is. Yeah.
Yeah, so you will get there, right? Anybody could do this. So, and Trey is probably going to be able to help you very well after this because he probably already knew all this, but this is probably locking it in for him. So once we go around, he'll be fast at helping you. All right. Let's.
So you can get any vector and just label it a hat, and it'll just follow that as like an axis. So-
Yeah.
it-
So you
okay.
could use. Yeah. Exactly.
Hmm.
So I think in the code, I should be careful. The code, it's actually literally that because R in the code was already a vector. It doesn't have the line over it, right? So to be clear, the thing that I first circled there, the thing on the top, that's how you think about it. That's how you would literally write that same thing in our code, right? I guess I am giving you all the answers here. Shit. All right. Well, there's one other one. There's one other one. What's the other component of acceleration we usually worry about?
A10.
Give me an equation.
R alpha.
Those are all scalars. Take a guess what we need to do. If I want it as a vector.
What's perpendicular to R? So how would you do that?
What do you think?
So this is where you would use a cross product.
Probably. And if you don't know which way to cross it, what should you do?
Try both. See which one
You know
works.
what I'm saying? Now, there's another acceleration that we could get. Once you know AC and a tangential, what else could you get?
A total.
How do you get a total?
That's R, and then square root of AC and A10 squared.
No, that's the magnitude of a total. How do you get a total? You see the difference there?
Hmm.
How do you get a total?
Well, on paper, we would do the inverse tan of both those.
No, you're thinking too hard.
Hmm.
Just add up the two components, right? Oh, you were trying to get it in polar. Is that what you were trying to do? Get the angle and the magnitude and stuff? Why? We're in coding land. And if at some point you're going to figure out the code for this, at some point you're going to figure out the code for this. Couldn't you then just literally take those lines of codes and add them together and you're done? Das flutscht, oder? Get your Schwäbisch on. Ja, don't you know, eh? That's like a bunch of weird languages all mixed together there. All right, so Jordan Olma Dern and a Masin. It's the only Turkish I know. It means, are you sure we're all out of yogurt? You could see the stupid things I spend my time on. I think, okay, whoa. I'm getting off topic. I'm losing my mind here. This is the guts of what you are supposed to do today. Now, the issue which, so I think you could figure this all out now. Any questions about it before I get rid of this? Anybody want to take screenshots? This is the time before I erase. Okay. Is that making any sense?
It makes sense.
All right. Screenshots going once, going twice. Sold. I'm clearing these annotations. All right. If somebody else needs it later, you get it from somebody who got it. Okay.
It's on YouTube anyways.
Oh, senior moment? Maybe. All right. There we go. Okay. So now let's talk about the last piece that Jose actually wanted to talk about. And I apologize for taking too long, but to be honest, you guys are usually so bad at coding. This will probably help you in the long run anyways, right? So if that means this took a little longer to get through, but you get through class, whoops, not that. Get through class better. Oh, I'm having trouble speaking. Whatever. All right. Now let's say you're going to do something like this. So I gave some of you imagine you have a pivot point and a square. And you want this thing and you want to release it from rest and it's going to swing back and forth, right? You know what it should do. Can you code it? Well, the issue here is you first need to figure out alpha, right? If you need to figure out alpha, how do you get alpha for this type of problem? What would you do? Somebody tell me. If we're doing it on paper, forget about the code. Just tell me how you do it on paper, and then we'll worry about getting it from paper to code.
Should we find the torque and inertia?
Torque and inertia, right? Because sum of torques equals I alpha. Now, in this case, how would you get the moment of inertia?
Square plate?
Okay, is it the same one you find in a table?
No, it's shifted the pivot.
So what do I have to do because it shifted?
Parallel.
What force causes the torque here?
Gravity?
mg. Where does mg act?
Center mass.
Ding, 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 ding. So you're going to need the torque from mg. And you're probably going to need to do a cross product to figure it out, right? Just like what we were just doing. What's the equation for torque in general? For an arbitrary torque equation, what's the general way to write torques? What cross what?
Or cross force.
R cross F. So this one, conveniently, they told us this. So you could have to figure out some kind of R vector crossed with some kind of mg vector. You have to figure out how to code mg as a vector. I bet you could do that. All right. So now from this, I think you could figure out alpha. Agreed? Once you do all that, then you could have your loop, and each time you get a torque, you get a new alpha. You do the same stuff that we just did, and you use the alpha to update omega and change the position. Once the position changes, which of these things change? We don't need this anymore, right? Let me just write this. Which of these things need to be updated inside the loop? All of them, some of them, none of them.
Torque and alpha.
Exactly. Moment of inertia is a property of the object. We're not changing its location relative to the pivot point. This you could calculate outside of the loop in your code. This one and this one need to be updated inside the loop. So the order in which you do things in general is always force, then you do momentum, or sometimes you could think of that as velocity, and then position. That's if you're doing, this is called the Euler-Kromer method. You update things force, then momentum, then position. By doing it in this order, your code will work. If you don't do it in this order, the numerical artifacts caused with floating precision will cause the oscillations to suddenly get out of control, and then it'll start doing this. That's not what we want. So the equivalent would be, what's the rotational equivalent to this order? 1, 2, 3. And then obviously the fourth thing would be t plus equals dt. What's the rotational equivalent? What's the order in which you have to do these things so that the code actually works? What's the rotational equivalent of force?
Torque.
So we're going to do torque, then we're going to do
Alpha.
what's the torque, which then you're going to do. So let's maybe say torque, then you do alpha. You could also update the
Angular momentum.
Angular momentum. If you update the angular momentum, that gets you the omega, right? And then you could update the what?
Angular position.
Yep. And then time. So if you want, I'm referencing one of your pages. This is kind of discussed over and over again, but I'll just reference it. One of the spots in the workbook. I mentioned this in there. At the bottom of page 97. No, that's not what I want. At the bottom of page 85, I have this listed. Or if you don't want to look for it, there it is right there. That's kind of the process that we need to follow. Woo! That live stream is over.